Okay, so there are a few other formulas in the growth and decay model. So we have a doubling equation, a tripling equation, and a half-life equation. So if you think back to our growth and decay, this one, growth, was a times 1 plus r to the t. So here, if r is 100%, it's 100% increasing. If I do 100% is 1, so 1 plus 1 would be 2. So 2 is our growth factor. Here, if it's increasing by 200%, 2 would be the r. 2 plus 3, or 2 plus 1 makes the 3 here. So that's the tripling effect. The half-life, so this is like a decay one, a times 1 minus r to the t. So half-life, r would be 50%. So 1 minus 50% is a half, and that's what we get here. So these are like special cases of the growth and decay. The only difference with these is now they have this p-value as part of the exponent, and the p is your period that it takes to do whatever it is you're doing, the period that it takes to double or triple or cut in half. So however long that is, that's the number you divide by. But everything else is the same. A is still your initial. R, we don't really need R because we already have the whole base, the whole growth factor and the decay factor. T is still your time. But now your time doesn't have to be in years. It can be in whatever the value is. The only thing is the period and the time have to match. So both of these have to be the same units. So time is either both in years, they're both in days, they're both in months, whatever. These have to be the same. Okay, so looking at example 5, a population of bacteria doubles every 3 days. So doubles tells me I'm going to use the base 2. So 2. If the initial population is 1,500 bacteria, how many are in the colony in 3 weeks? Okay, so let me just start off. So N equals A, so we're using this formula. A is your initial amount, which is the 1,500. And since it's doubling, that means the base is 2, so times 2. And then we want to know the time that it takes, or the amount that they have after 3 weeks, if it takes 3 days for it to double. So notice we have different units. We have weeks and days. So we need to convert these to the same. It's probably easier to convert this one to days than it is this one to weeks. So right here, if we do 3 weeks, each week has 7 days, we get that there's 21 days here. So this is the time that we want, 21, if it doubles every 3 days. So the 3 days is our period. So 3 here. So technically our exponent is 7. So again, just go type this in the calculator. 1,500 times 2 to the 7th power. And we get that there are, let me write this down and then I'll say what it is. 192 and then 1. Oops, I put too many zeros up here. So 1,500. This is 15,000. 1,500. And it's still 192, but now there's only 3 zeros. 192,000, and then we're talking about bacteria here. Okay, so it's still the same as the other ones. The only thing is you don't need to know R. If it's doubling or tripling, you're basically already given R. All you got to do is plug in the other values that it needs. Okay, so if we look at 6, a culture of bacteria triples. So we're going to use the triple formula. Every 8 hours, that's your period. If there are 100 bacteria now, how many will there be after 18 hours? So N equals, the initial bacteria is 100. And we're going to use the tripling 1, so times 3. T is the time that we want, so we want 18 hours. And the period is 8 hours, so they're both in hours, so we can just put 18 divided by the period is 8. And again, just come over here and type it in. So 100 times 3 to the, I'm just going to do 18 divided by 3 up here. Or not 3, divided by 8. And we get this decimal, 1184.47. But since we're dealing with bacteria again, we round to the nearest whole number. So 1,184 bacteria. Okay, so when you're given a population, you round to the nearest whole number. Okay, and then the last one, the half-life. These deal a lot with decay, so radioactive decay of a substance. So here the half-life of carbon-14 is 5,730 years. So that means it takes 5,000 years for it to cut in half. However much carbon is there, half of it is gone in 5,000 years. It's kind of why they use carbon for carbon dating of old stuff, because it takes a long time for it to go away. Okay, so here we're going to use the half-life. N equals, a plant contains 100 grams of carbon-14. How much carbon is left after 2,000 years? So the 100 grams is what we're starting with. So 100. And then we want a half-life that it takes for 2,000 years. So 2,000 is my time. So 2,000 here. But the period that it takes to cut in half is this one. So this is P. So divided by 5,730. So again, it's not even going to be half of this because it hasn't reached the 5,000 years. That's a way that you know whether your answer is accurate. So 100 times, oops, too many zeros, half, to the, and I'm just going to go ahead and write all this in there. 2,000 divided by 5730. And we get this one. Can we have decimals? We're talking about how much, and we're talking about grams, so it's okay to have decimals. So we can do this 78 point, maybe like 2 decimals, 51 grams. So for grams, it's okay to have decimals. For population, not so much. Okay, so those are 3 formulas that are an extension of the ones we've been doing. The other part is going to be the E. So here, talking about the E value, last time we did the money for all these situations, and we noticed that even though these numbers were getting bigger and bigger and bigger, the money wasn't getting so much. It got a little bigger, but not too much. So again, notice from the account that we did, it will not continue to increase even though the number of times it is compounded continues to increase. This is called the limit of the function. So that's like a calculus word, limit. So here I'm going to show you what this number approaches. So let's assume everything's 1, the rate's 1, the starting amount is 1. We're just going to change the n value. So first we're going to plug in 1s for the n. For annually, that means this is 1, this is 1, and then we can figure it out. So 1 over 1 is 1. 1 plus 1 is 2. 2 to the 1 is 2. And 2 times 1 is just 2. Okay. I mean, that's the only one I'm going to do here. The other ones I'm going to do in the calculator. But that's what we're doing. So the next one, semi-annually, we're going to plug in a 2. And then we'll plug in 4, 12, 52, and daily is 365. Now for these two, I'm going to have to calculate them. Hourly means every hour it is compounded. So I need to, every hour in the year is compounded. So I need to take the 365 and multiply that by however many hours there are in a day, which is 24. And I get that it will be compounded 8,760 times. Minutely, well, I take that number and multiply it by the number of minutes there are in an hour, which is times 60. And in a year, there are 525,600 minutes. So I'm going to take each one of these and plug them in to this formula for n. So the first one, 1 times 1 plus 1 over 2 to the, close that, oops, not that one. Close this one and then exponent to the 2. And I want these as decimals, so menu, oops, not fraction. To convert to decimal. Right, so here I get that this is 2.25. And I want decimals here because I want to see what's happening as it approaches. Okay, so I'm going to plug these next ones in the calculator and just get the decimals. And then I'll do the last 3. Okay, so what I've done is I've plugged in 4, 12, and 52 in the calculator. So if we write the 4th one down, so for quarterly, we get 2.4414. For 12, we get 2.61304. I'm not going to write all that. And then for 52, we get 2.6926. So again, we're going to get these last 3. And it's going up slowly, but it's slowing down. So these aren't going up by much. So getting those last 3. Okay, so then 365 is 2.71457. Hourly, the 8,760 is 2.71813. So again, you can really start to see that it's becoming the same number. And then the minutely, we get the 2.71828 number that it approaches. So again, I could go secondly, but it's not going to be very much different than this number right here. I mean, it's probably not going to be any difference if I'm rounding to 4 decimals. So notice these y values, they're getting higher and higher and higher and higher, but they're kind of flattening out to this number. So we say that the limit of this exponential equation is 2.71828. This number is kind of like pi. We call it the natural base number. And we use the letter E, little cursive E, to represent this number. So it's like any other irrational number, so it's kind of like pi. It's not going to repeat. I know it looks like it starts to repeat, but it's not going to continue that. It's going to keep going. And there's a lot of real-world applications that happen that can be modeled by E. That's why it's called the natural base. Next year in pre-cal, right now we have 4 formulas. We have the 1 plus n, 1 minus n, or sorry, 1 plus r, 1 minus r, this nt1, and then the PERT. In the end, they all become PERT anyways, because most things change all the time. Every minute, every second, things are changing. So this one, the E function, is the one that's going to be more transferable and the one that you're going to use next year. Okay, so we're just going to do a few things with the e here. The natural base e can be treated like any other base. All properties of exponents, transformations, and graphs act the same way. So that's what this last little part's going to do. Alright, so here we have 4 problems with exponential properties. So it says simplify the following, then evaluate the expression with the calculator. I really don't care that you do the calculator part, but you should know how to simplify these with our properties of exponents. So here, this exponential, the base is e. Here the exponential, the base is e. When bases are the same, we can add the exponents together. So here we're going to add 6 and 3 to get 9. Coefficients we treat like normal though. The 2 and the 6, because it's all multiplication, we're just regrouping them. We multiply that and get 12. I'm going to do it in the calculator, but I'm not going to write it here because these numbers are going to get pretty big. So here I can do 12 e to the 9th, and I get this one with some decimals over there, but it's not showing the decimals, so I'm not going to write these down. The important parts are the properties. Okay, so looking at the second one, here the bases of the exponential are e's again. So e. When we divide, we subtract exponents. So here we're going to get e to the 4 minus 6 is -2. But coefficients, we do what it says. It says divide, so we divide. 12 divided by 3 is 4. Now we don't leave negative exponents there. Any negative exponents, remember negative means the reciprocal of, negative exponent means the reciprocal of. So this part is going to end up flipping to the bottom and become +2, and then the 4 stays in the numerator. So negative exponents just mean flip the reciprocal of and make it go to the denominator. Alright, so for part C, we have an exponent on the outside. So we have to apply that to everything in the inside. So when we apply it to the 4, we get 4 squared. And when we apply it to the e, a power to a power, we multiply these. So here we're going to get e, 3 times 2 is 6. So this one's just going to simplify to 16 e to the 6th. And again, I'm not going to worry about typing that into the calculator. They're all going to be decimals, and they're all going to be pretty big. Maybe that one's not so big, but these will be pretty big. Okay, the last one is the combination. So here, first, we're going to combine like terms in the numerator. So we're going to leave the denominator the same. I say combine like terms. It's not really combining like terms, but it's like combining like terms. Okay, so we combine the e's together. Since we are multiplying, we add these. So we're going to get e, 5 plus 3 is 8. The numbers we treat like normal though. The 8 and the 3 we multiply to get 24. So now vertically we can combine them. Numbers we treat like normal. 24 divided by 4 is 6. And then exponents we subtract. 8 minus 2 is 6 again. Okay, so you really don't do anything different with e's than you do with other numbers, except that you can actually type this in and get an answer in the end. If it's an x, that's all you can do. But with e's, you can actually take it a step further and get values. Okay, so same thing with graphs. Not going to be much different here. So we still have a growth function. We still have a decay function. If I give you y equals e to the x, this is basically, since e is number 2.71, how far do I want you to go? Okay, I'll have you go that far. So that's how far you have to know it. So since it's that number, it's always going to be that number. We really don't look at the base to know if it's growth or decay. We have to look at the exponent. Because e will always be e. So here, if I say y equals e to the x, I'm basically saying y equals 2.718 to the x power. So this one, since it's a positive number, and since the exponent's positive, it's just a 1 there, this is exponential growth. This is a growth function. So if the exponent is positive, then it's growth. If the exponent is negative here, so the negative, remember, means the reciprocal of. So this one is basically saying y equals 2.718 to the negative x. The negative means it's going to be y equals 1 over 2.718 to the x power, which this is less than 1. So here the negative exponent means the base is less than 1, so this would be a decay function. I don't expect you to know what the reciprocal is. If you really want to know, you can go type it in. So here, when I do negative x, that means 1 over. So e to the negative 1 is, this decimal for the 1 over is 0.367879. I'm not going to write that, but that's basically what this is. I just know that this is less than 1. So it has to be a decay. So for these, we don't really look at the base to know if it's a growth or decay. We look at the exponent. The base is always going to be e. That part's not going to change. The exponent is what changes. Positive exponent means it's growth. Negative exponent means it's decay. Okay, so that's what we're going to do for this one. We're going to say if it's growth or decay. And then transformations are the same as any transformation. So the transformation equation, so transformations, is a, h, and k. So basically we're looking at a times e to the x minus h plus k, because the base is always e. Okay, so if we look for growth or decay, we're not going to look at e, because e is always 2.718. We're going to look at the exponent. So here, the exponent is 0.25. So I don't care that it's a decimal. I care that this number is more than 1, so greater than or positive. So I'm going to say this number is positive. That means it's a growth function. I don't care that it's a decimal. That's fine. It's still going to be a number bigger than 1. Here, the exponent is negative. When I distribute it, it's going to be a negative 3x. So since it's negative, that's going to make it decay. So again, if you don't believe that, you can go to your calculator and you can actually see what these numbers are. So if I do e to the 0.25, I get 1.28. 1.28 is bigger than 1, so it has to be growth. Here, if I do e to the negative 3 for that part, I get 0.049, which less than 1 makes it decay. So I'm going to go ahead and write that. So here, for this one, the base for the 0.025, or 0.25 here, makes it 1.28, which is more than 1. Here, the base is when I make the negative 3 and the exponent, 0.049, stuff, which is less than 1, which makes it decay. Okay, so for these, it doesn't matter what you look at. This is what you're going to see more often. With e to the base is e, so you're going to have to look at exponents. But everything else is the same. So the k value is the number added to the outside, so this is k, which tells me my shift up and down. So this makes it go up 7. This makes it go up 1. these numbers also give me my horizontal asymptote. So horizontal asymptote would be y equals 7 here, y equals 1 there. It's not asking for that, but from what we did last week, it's the same thing. Okay, the h is still the number with the x here. So this is the h. Don't worry about distributing, you don't distribute. The -2 is going to make it shift right 2 units. This one has no plus or minus, so this one's not going to shift right, left or right. And then the a value in the front stretches or compresses it. So here the 2 is going to vertically stretch by 2. And here the half is going to vertically compress by half. So again, not much different than what we did with other exponential growth and decay functions. Just knowing that here most of the time the exponent is going to be the negative part, not the base. The base is going to be e. The exponent will be what tells you growth or decay. Okay, and then the last one for these special e functions. And again, next year in pre-cal, this is what you're going to see most often. All bases can be changed to e, and that's the one we're going to use because that's the one that's more applicable. Alright, so here, the management at a factory has determined that a worker can produce a maximum of 45 units per day. This model indicates the number of units y that a new employee can produce after T days on the job. So this is a transformation that we just saw. It just looks a little weird because the k value's in the front. So if it helps you, you can rewrite this as y equals negative 42, that's the a, e to the negative 0.05 t, and then this 45 you can just, this is your k value, so you can just put it at the end. Sometimes you'll see that with the k added to the front, but here we just move it. Okay, so is it growth or decay? So first we look at the exponent here. Here the exponent is negative, so that's going to tell us, negative exponent tells us that it's decay because the exponent is negative. However, like we talked about when we did transformations of just any function, since the function itself is negative, that's going to make it reflect over the x-axis, which takes this and switches it to growth. So yes, it's decay because the exponent's negative, but then it turns to growth because it's reflected. And I'll show you what this graph looks like in just a second so you can see that it's actually growing. Okay, but this part B we can actually do without a calculator. These two we're going to need a calculator for. So here, how many units can be produced by an employee on the first day? So notice here, T is after T days on the job. So after they've been on the job for this amount of days. If it's your first day, you haven't been on the job yet. So for this one, T is 0. So if we plug in 0 for T, we get y equals negative 42e. 0 times anything is just going to make this exponent 0. Plus 45. Oh, what is e to the 0? Anything to the 0 power, including e, is just 1. So here, this is really going to go away, because 1 times negative 42 is still negative 42. So here we just do negative 42 plus 45, gives us that y equals 3 units on the first day. Okay, so that one, I mean, I know what e to the 0 is 1, so it's not going to change, it's not going to It's not hard to figure out the answer without a calculator, but I don't know what these numbers are. I don't know what e to the 13th is, so that's what I need a calculator for. So here for part C, I'm going to go ahead and write the equations for these and then get the calculator out. So how many units can be produced per day by an employee who has been on the job for 13 days? So after 13 days, so here T is 13. We're going to plug in 13. So we're going to do in the calculator y equals negative 42 e to the negative 0.05 times 13. And then add the 45. So we'll plug that in the calculator and estimate the number of units. And we are rounding to the nearest whole number here because you produce a unit or you don't. Okay. So then the last one, we're going to use the graph to find the intersection again to figure out how many days of employment are required for a worker to produce 30 units. So the 30 for this one, 30 units here, is giving me the y. So we're doing 30 equals this equation, negative 42 e to the negative 0.05 x, because that's what I'm looking for, plus 45. Okay, so let's do the one where we plug it in first. So here, all we're going to do is plug the 13 in. Negative 42 times e to the negative 0.05 times 13. Get out of there and do plus 45. And we get that decimal. We're talking about units here. So we can just say that y equals, to the nearest whole number, would be 23 units. Okay, so if I'm looking for the number of units, I just plug in the answer. Here I'm given the units, so I have to solve for the exponent. We don't know how to solve for this by hand, so we do it with the graph in the calculator. So here I'm going to go get a graph. So new graph. And in the first one, I'm going to go ahead and plug in my function, negative 42 e to the negative 0.05 x. Get out of there, and then plus 45. So this is why it's growth, because it's increasing. Even though it's going to end up flattening out, it's still increasing from left to right. The decay is because of the exponent, but then I reflect it to make it growth. Okay, and I want to know, when is that equal to 30? Now this one I should be able to drag fairly easily. There we go. To get the intersection. If you need a good window, I can just tell you over here. If you go 0 to like 60 days on the x, and then 0 to like 60 on the y, you'll see a pretty good shape. So here, this one is going kind of this way, and then my 30 is kind of like this. So remember, in the calculator, I want to go to get intersect, go a little bit to the left, and a little bit to the right. So the intersect button, menu, you're going to go to analyze, and then number 4, a little bit to the left, a little bit to the right. And it tells me that x equals, which is time, 20.6, but time here is in days. So here it would be okay just for me to round this to say 21 days. So here x is 21 days. So after 21 days on the job, they'll be able to make 30 units. Okay, so these are, like I said, more applications are more with the E than the other bases. Any base can be changed to E, so that's why we just normally use this one. And eventually everything's going to be E, because most things grow continuously. It's not like they just say at the end of the year grow. No, they're growing all throughout the year. So eventually this equation is the only one that we use.